Welcome back. So have I scared you yet? Have I scared you yet, or are you still looking forward to playing with pointers? I know that there's a lot of things that are rough-edged about them, but they're really powerful and they're really fun. Let's actually talk about how to use them effectively. So remember before I mentioned that variables, you declare them int x, and now x is always going to be an integer for the rest of the life of the program. But pointers can actually move around a little bit. If I say pointer int star p, it means I'm going to point to I can move it to point to this integer, and then next line point it to that integer. So that's actually easy to do and doesn't require any trouble. You can, in fact, declare a pointer to a generic type, which is called, you declare it a void star pointer. And that means you could actually, with some more type casting, which we'll talk about later, I can then move it around. Now it's pointing to an int. Now I'm going to point it to a float. Now I'll point it to a char. And you got to really know what you're doing. And usually that's not what you want to do, and so you probably typically not do that. So that's kind of expert mode only. But you can do that if you typecast it right. You can even have pointers to functions. The picture at the bottom right shows a pointer to a function. This says I'm declaring this function pointer, fn, okay, function pointer, to be a pointer to a function that takes two void stars, two generic pointers, and returns an integer. And foo is one of those guys, okay? Foo satisfies that. So now that means that and that declares, that actually makes the link to it, okay? Address of foo. So that pointer now, fn in a way, points to foo. So if I actually want to make use of that pointer, I'd say star fn, and then open paren x and y. So that's the same as calling foo of x and y, is star fn x and y. In fact, I'm going to show you an example of doing this to try to write the higher order function map a little later. That's pretty cool. So we talked about structures before. You've seen that before. Typedef, a point. This is like the hello world of abstract data types. Make a point. Make a point class. Make a point structure in C. So it has two fields, x and y. I can get access to them, and I make two here. I'm making 2 points, P1 and P2. Each of those themselves have two fields, bloop, P1 and P2. P1 has x and y. P2 has x and y. Point star p address says, I'm going to make this p address be a pointer to a point. It doesn't point there yet. The next line says p address now equals address of P2. Now p address points to P2. So now what can we do? Well, the first line dot notation says I can int h equals p1.x. That's fine. That just grabs it before and sets it to h. I can also set, p1.y equals p2.y. Nothing special there. I can also use the pointer and arrow notation. So I can say p address arrow the field name. So p address arrow x, and that just basically follows the pointer to whatever point it is. Happens to be P2, but who knows? And then what's the x field? Grabs that and stuffs that into h. You can also do something interesting, which is, that star p address is kind of like the point itself. So if you have a parens around star p address, you can then use dot notation. Now, almost everybody, 99.9% of people, if they have a pointer to a structure, you use the arrow notation. But you could also use the dot notation as well. If you say P1 equals P2, that says pointer P1 gets the values of P2. That's actually pretty interesting. So that actually copies the value. That does not say sharing. That says get the values of P1 and put them in. Now P1 and P2 have exactly the same x's and y's. That's not a pointer. That's not a sharing of the same storage. That's two different storages, each of now which have the same values. That's really important. It's different than a lot of other languages. Kind of cool. You have a null pointer, the pointer of all the point. Remember that null was a special thing, and a pointer that's null means it points to nothing. It's the only kind of safe thing you can declare it as. Okay, how do you initialize something? You have to have a kind of a sentinel value, and null is the sentinel value of pointers. Null means 0, which really means I can never have anything stored at 0. Remember this infinite array of memory? Well, 0 is reserved, never have anything valuable there. Okay, so that's important. If you ever try to read or write a null pointer, that's bad. If you're trying to follow a null pointer or get its value, you can't do that. So that's trouble. So, but it's a way you can protect it. You say, well, is p equal null? Then if it is, I'm not going to touch it. It means I didn't get some storage, or it's null. It's not valid. I can't use it to read or write any values. You also remember that 0 is false. So now I can actually say if p and q are pointers, I can say, if not p, meaning if not p, that means only if p was 0. That's not true. If p is so if not p, that's only true when p is 0. I have to make sure I say this right. So that's cool. That says if not p, that's a way to say, p equals null is the same thing as saying if not p. If I say if q, that's true only if q is a good pointer. So you can use the fact that pointers are 0 when they're bad, when they point to null, and non-zero when they're good, point to some actual data as a useful test in your code. You can point to variable things. As I mentioned before, you can have pointers to shorts or to integers or characters. Modern machines are byte addressable. In the olden days, they were word addressable. Now they're byte addressable. I can get access to every byte. Okay, that's kind of useful. And a C pointer is just a way of thinking of an abstracted memory address. It's our way of interfacing with memory. When you have type declarations, it's a way of telling the C compiler, this is how big these things are, and this is how much data should be moving back and forth from two pieces. But we actually want what's called word alignment. And word alignment means that most machines are really fast if whatever the word size is. We mentioned before, word size is kind of the generic size of your address space. So if I have a 32-bit machine, that means my address space is 32 bits. I can access 2 to the 32 different memory points. And it also means that the data channels are almost always going to be 32 bits moving around. It doesn't mean I can't move a 64-bit value, it just means I'll do it twice. If my main channel, if I made like 32, it's like 32 lanes, okay? I can still send 64 cars, just may have to do it twice, and that's internal to you. If you happen to have things be word aligned, that means everything has to be aligned to whatever the size of your word is. If a word in the machines we're going to use is 32 bits, that's 4 bytes, which means things have to be aligned on 4-byte values. So that means you can store it at 0, but you can't store anything. Let's say if I can store a character anywhere, that's true. But if it's a larger value like an integer or a float or a short or something, you can't, short's are weird because it's my half. Let's talk about ints for now. So if I have an int, 32-bit machine, I can't store the int like this. I have to store the int exactly aligned with that. So word alignment says you have to be aligned to 0, which means the address of the int has to be 0 or 4 or 8 or C. If you look at the hex value, the hex digit, the nibble, that's going to be 0, 4, 8, or C, and then 0 again. So if I actually ask you what the address is, if it's word aligned, it's always going to be 0, 4, 8, or C. It's kind of a cool thing. Here's an example on the right of a nice picture that shows a short, which in this case is going to be 16 bits wide, and there's a pointer to that short. It happens to live there. This is an integer, this is x, a pointer to x, and you see that it lives at 48. Again, that's a multiple of 4, so we're good there. And it's a character that can live anywhere, so that's kind of a nice thing. Okay. Size of is an operator you're going to see used a lot later when we talk about reserving memory from preserving space from your memory system. And size of any type is going to tell you how many bytes wide that type is. So size of car is 1 by the definition of C99. But remember, you don't know how big size of ints are. So you actually can go to a new machine, a great program to write on your first machine you just, encountering. Someone drops a new machine, I just invented a new machine. First thing you write is printf size of int. How big are the ints there? How big are the doubles? How big are the longs? That little table I showed you before had like long, int, shorts. Do a whole table that says, in this machine, shorts are printf %d size of short. Ints are print %d size of ints, and you keep doing this. So actually it'd be kind of neat to play with that as you move that, as you ported, we learned that word porting, that code to different machines. It'd be kind of fun to see what the output of that was. This is why int types exist, so that you don't have to kind of guess what the size of those guys are. But size of is really useful to find out how big they are. You can also pass in size of a struct type. And a struct type says, oh, I make this struct that has an integer and it has a character. That's 4, standard machine, and this is 5. If I say size of struct, is it going to tell me 5 or is it tell me 8? Does it actually make sure the struct is word aligned? So does that mean even if I only use a character, does it actually going to use up that whole int, even though I only use one of those 4 bytes, is going to use up all 4 because it has to be word aligned. So you can ask size of an int plus a character to see whether they actually make sure you word align all of your structs as well. Okay, we'll see size of a little bit later, and we'll learn more in the next video.